Hello guys, welcome back to learning microcontrollers. In this video I'm going to show you how to interface a potentiometer with a PIC16F877A microcontroller using formula method. In my previous video I showed you how to interface it using a polling method. Now I will show you how to use a formula method for the same purpose. So let's get started. This is our PIC16F877A microcontroller, 40 pin, it's a DIP version. And this is the potentiometer I am talking about. It is also available in high precision format as well. You can buy many type of these having 3 pins, 2 input, 1 power, 1 ground and 1 variable pin. But I am using this cheap one. It is not very precise but it will do the task. So let's get started. As you can see, it has 3 pins. I name the right one, if you hold it like this, as ground, the left one as the power. Now you can shuffle these 2 pins, doesn't matter. You can make the right one VCC or you can make the left one ground. What it will do is it will only change the direction. That when you go clockwise it will increase the voltage. If you go opposite, then when you go anti-clockwise it will increase the voltage. Else potentiometer will work fine and its programming will work fine. But clockwise and anti-clockwise will be inverted if you shuffle these 2 pins. Now the center pin is an ADC pin. It's a variable pin. So let me show you how to connect it with a PIC. First of all, you connect ground directly with the ground of the PIC, VCC with the VCC pin of the PIC, and ADC you can use any available analog to digital channel of the PIC. I am using pin number A0. So you can use any other pin, any available pin like A0, A1, A2, A3, A4, A5, E0, E1, E2. You can use any of these pin. So guys, now our potentiometer is connected with the PIC. Now we need an LCD to display the output. I am using this LCD. This is LM016 16x2 LCD having a backlight. You can use any other form of output like 7 segment or any other thing you want, but I am using this. Now as you can see, this LCD has 16 pins if you hold it like this from left to right. Now to interface this LCD with the PIC, you need another potentiometer. This potentiometer will be used to adjust the contrast of the LCD. Now let me show you how to do the wiring. This potentiometer has 1, 2, 3 pins as labeled on it. So the pin number 1, and this LCD has 16 pins as you can see, 1 to 16 from left to right. Now you connect pin number 1 and 5 of the LCD and you connect it to the pin number 1 of the potentiometer, then you send it to the common ground of the PIC. You connect pin number 3 of the LCD with pin number 2, that is the adjustable pin of the potentiometer. Then you connect pin number 2 of the LCD with pin number 3 of the potentiometer, then you send it to the common 5 volt VCC supply. Now pin number 4 is your RS pin. You can use any available digital input output pin of the PIC for this. I am using pin number 50, that is C0, that port C, pin number 1. For pin number 6, that is the enable pin, I am going to use pin number C1. For data pin 4, I am going to use pin number C2. Or for pin number 12 of the LCD, that is data pin 5, I am going to use pin number C3 of the PIC. For data pin 6, D0. For data pin 7, D1. Now this pin 15 and 16 of the LCD are for the backlight. If you leave it here, still your LCD will work, but it will not show the backlight. Now to ensure that you have the backlight, you connect pin number 15 with the 5 volt supply of the PIC and 16 with the ground. You can use any available 5 volt source. So I connect them to the same source because they work on the 5 volt. Now this pin number 7, 8, 9, 10 of the LCD, they are for the 8-bit mode while we are using 4-bit mode. So they will go empty. Now guys, what I'm gonna do is that I will program the PIC in such a way that whenever you rotate this potentiometer, it will show at how much degree it is rotated. So sorry, how much percent? 64%. If you rotate further, it will say 72%. And if you go in the opposite direction, it will say 52%, 32%. To inverse the direction, you simply shuffle VCC and ground pin. So guys, let's get to our Proteus demonstration. This is our Proteus guys. Let me zoom it in. Okay, you go to the devices section here and you click on this small P. You get keyword right here, PIC16F877A. Place it anywhere on the screen you feel comfortable. Now go back to the P again and write LM016, that is our LCD. You place it anywhere on the screen like this. Now go back again. We need a potentiometer. write down variable resistors. Here you go, they are variable resistors. Select any as you like. I'm using the 10K one, third one, this one. You take it and place it anywhere you like. One here, that will be the one we will use as sensor, and one here, this will be the one for the LCD's contrast. Here we go. Now go to this terminal mode, take a common power source and place it above, and then a common ground source, which will add, these both will act as the common ground and power of the circuit. Now we do the wiring. You connect this to the one end of the variable resistor, like in both cases, and the bottom end of the both of the variable resistor will go to common ground. Here you go. Now it's connected to the common ground. Now this is adjustable one, and we can use any available ADC pin of the PIC. I had used A0 in the presentation, so here we go. Now 1, 2, 3, all three pins are connected. One to the power, one to the ground, and one to the ADC pin. Now next thing is we connect the LCD. Now let's do as shown in the presentation. 1 and 5 pin gets common and go to the common ground. So this is the common ground. Then pin number 2 will go to the power, 5 volt. Here you go. Pin number 3 will go to the adjustable pin. This is the adjustable pin of this potentiometer. So we take a wire and connect it here like this. Now RS pin we are using C0. Here is our C0 in the Proteus. Enable pin will go to C1. Here is the C1. D0, D1, D2, D3 will go empty. D4 goes to C2. C2 is here. Here is C2. And C3 goes to D5 here. Now D6 goes to D0 here, and D1 goes to D7. In this way our connections in Proteus are complete. Now guys, we get to our MikroC for PIC programming. So let's open the MikroC for PIC. I'm using this version 5.6.1. You can use higher versions as well. There is a little bit of difference in the coding, like you need to write some capital letters. For the delay sector I will tell you. Let me zoom it in. Okay, here is our MikroC for PIC version 5.6.1. Better use the same version. It is a good version, stable version. Okay, now here you go. Welcome to the new project wizard. Click on next. Write the name of the project. Potentiometer formula method LM learning microcontrollers. That is what I wrote the name. You can write any name as you like. Then I select the microcontroller PIC16F877A. 20 megahertz is the crystal I am using. Click on next, 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 and finish. Now first of all we will need to initialize LCD before doing anything else. So for that purpose you go to library manager. Here you have something called LCD. You click on it and you select the LCD. In the LCD you have here this LCD INIT. Click on it. In the LCD INIT, as you can see in the example below, you have these commands. You copy them till here, not the bottom, and then you place it above the void main loop in the main programming like this. You place it here. Now as you can see, this is RS, this is LCD pinout setting, and this is the direction setting. First of all, in the pinout setting you set your RS pin as you had decided to take in the current project. I had taken C0 for RS as shown in presentation, C1 for EN enable pin. For D7 I am using D1, for D6 D0, and for D5 C3, and for D4 it's C2 like this. Similarly for the pin directions do the same. For RS pin use C0. I am using C1 for enable, D1, D0, C3, and C2. Now the pins of our LCD are also initialized as needed. Now we can initialize the LCD. To initialize the LCD in the main code, write down LCD INIT. This command initializes the LCD, also gives some initialization delay. 100 milliseconds will be enough. In this version You can go with smaller d as well, it will not give the error, but in the higher versions of MikroC for PIC, you have to make sure that this d is always capital, else it will not work. You can go with smaller I as well in this version, it will work fine, but in the higher versions of MikroC for PIC, you have to write this in a proper format. So guys, that is not a big difference, you can make the changes if you even are using a higher version. Now we have our LCD initialized. Other than LCD, we need an ADC port. So for that, we initialize the ADC pins of the PIC using this command. This command initializes all the ADC pins of the PIC. Now you can use the ADC channels as you like. Now before we continue, we need to remove the cursor of the LCD. We do not need the cursor in this project. If you want to use, you can use, but I don't need it. So for that, click on this LCD CMD here. Now in the LCD CMD, you copy this command in the example, this command only. Place it below where you initialize the ADC pins here. Now go back, click on LCD CMD again, and now in the available LCD commands below, search for turn off cursor. This is turn off cursor command. You copy it, you go back and you paste it inside this bracket. Now this will turn off the cursor. Give some initialization delay. 100 will do fine. Now apart from this, before we go to our forever loop, first of all we should clear the LCD. If there are any rack-backed values, they will get cleared before the program runs. So for that, go to LCD CMD command, again copy this command, this time LCD clear, that is already written, so this is fine, it will clear the screen. Now your screen will be cleared, your LCD will be initialized, ADC pins will be initialized, cursor will be removed, and we are good to go for the forever loop. Now for the forever loop, write while 1. Forever loop starts here and ends here. First of all, we need to take value from the sensor before doing anything else. For that, we will need a variable which will store the value. We take a float read 1. It will store the value of the sensor, but we cannot display floats directly on the LCD. We need to convert them to a string. So we also initialize an array of char, which is a string, like read 11. How much big? 5. Like it can store 6 digits, 0 1 2 3 4 5. It will be 6 digit string maximum. So 6 are more than enough for our numerical value. So we go down and we write the command to read. Read 1 is equal to ADC read 0. Why I wrote this is the command and this 0 is the pin. We are using pin number A0 as I had shown you in the presentation. If you use the pin number A0, you write 1. For A1 it's 1, for A2 it's 2, for A3 it's 3. Likewise you go till you get to the last pin. So I am using A0, I wrote 0. If I was using A2, I was to write 1 2, pin number 2, that is channel 0. So now we give some initialization delay before we continue. Here we go. Now we need to convert this value to a string because LCD cannot display floats directly. So write down float to str. This is a command, read 1 to read 11. Now whatever is in the read 1 will be converted into read 11 as a string, and now we are eligible to display it on the LCD. So give some initialization delay. 10 will do fine. Below that we display it on the LCD. Use this command LCD out. First start writing from first row, first column. What it should write, read 11, like this. Like this. Now give some delay for how long the value should be written before getting overwritten. 100 milliseconds or 200 will be enough. So this is the code to get values from the sensor. So guys, before let's see if there are any errors. So we had made a mistake in the float to string. Float it's 2, like this. Yes, now it's good. Now we rebuild it, the code. See for errors. Okay, it's built successfully, no errors. First of all, I run this code on the Proteus and show you how it works. You go to our Proteus here, double click on the Proteus. We have 20 megahertz crystal as defined in the programming. Here you select your code. I had stored it on the desktop. This is the LM coding folder. This is the code. Click on OK, click on run. It will run the presentation. See, it is showing 510 value. not in percentage, because we are just taking a random value like our resolution. Now see here, potentiometer is in the center. This is in the center, right? As you can see, this arrowhead is in the center. It shows that variable is in the center, like total 102 power 10 is the resolution of the PICs. You can say ADC, and maximum 1024 it can show. So it's at 510. It's like half the value. Like half of 1024 is nearly 510, because there is plus minus 5% tolerance. So it is doing fine. Now we go to our hardware and do the same. Let's see. Guys, this is our hardware I am using here. This is our PIC16F877A. You can see in the top. Then I have a PIC kit. Then this is the LCD we are using here. This is the LCD. And this is our potentiometer, as you can see. Now first of all, we run this new code. Go to PIC3 programmer software. In the PIC3 programmer software, you click on file and import the code you just wrote. Here, this is a code. Click on write. Okay, the new code is being written, as you can see. Let's see what happens. It should work as it is working in the Proteus. So let's power it up. Click on. So it is showing the same values. Like now we are having an actual hardware here. Now what I am going to do is that I am going to rotate this potentiometer here. See what happens. See, it is showing the values, because in the simulation that is fixed, not variable. You cannot like move that, because simulation software do have limitations. While in the actual hardware, see, maximum it can go is 1024. Now minimum, as I rotate, it goes down. As you can see, it goes down. Minimum it can go is like 0. So it will not reach the exact 0 because of the tolerance that this cheap potentiometer has. The good potentiometers you buy from the market have better results. They can reach the 0, and they don't show rack back values. They are very, you can say, smooth. So for this project, basic understanding, you need this. See, it is working fine as needed. Now what we do is that we need to convert it into percentage. So we apply our formula. Now go back to the programming. In the programming, after where you had read the value read 1 ADC read, we need this to be applied to a formula. So for that, we need another float variable which will store the formula. Read 2, it will store our formula. Now we go back and let me show you. We use the formula. That formula is like, in the schools you obtain some marks. Obtained marks divided by total marks. This is the formula you use to calculate your percentage in your school results. Multiply by 100. It gives you percentage of your total marks, of your obtained marks. Obtained marks, like this. See, obtained marks divided by total marks into 100. Now here in our case, read 2 is equal to, what is our obtained marks? They are read 1. The values read from the sensor is our total result. Now the total is the highest resolution of the PIC, that is 2 power 10 equals to 1024. Is the maximum, as you had seen in the hardware and on the Proteus as well, is 1024. Now multiply it by 100. This will give us a percentage value. So let's try this. Before that, give some initialization delay. 10 will be enough, like this. Now we build this code and run in hardware and also on the Proteus. First of all, we go to the Proteus. Here we go. Now we click on run. Okay, I think the code is not correctly build. Click on build again. It sometimes happens. You have to, no, sorry, it's right. We didn't made it read 2 like this. You have to make it read 2 because it was converting this value to string. We need now to convert this formula value to string. Now go back to Proteus. Sorry for the mistake. Now you click on run. Showing 512. Click on build. I think I forgot to build again. See, now it's working fine. I forgot to build. So what is happening is that now it's showing 50, means it's a percent, 50%. Now we go to our hardware, we build the same code on the hardware, click on write. Now the new code is being burned on the hardware as well. Let me show you the hardware. See, the new code is being written. Wait, okay, as you can see, as in the presentation, it is doing exactly what we needed. Now let me move this potentiometer. Now it is no longer showing value from 0 to 1024, 1024. Now it had converted into a percentage like this. See, the more I rotate, the more higher it goes, and its accuracy depends upon the accuracy of this potentiometer. This potentiometer is this much accurate. It is not a very high quality potentiometer. It is a very cheap potentiometer. Costs few cents. You can buy a better potentiometer costing about $2 to $3. They will give you very good results. Very good. See, the maximum it goes is 100. Like it's like we had converted it into a percent. But as shown in the presentation, guys, I told you in the presentation that we will be showing you a percentage sign. Like this will not be like this. There you will have percentage symbols. Like there will be a percentage symbol on the screen. So we do that. We go back to our programming. Now to display a percentage symbol next to the value received, first of all, we need to add here. Oh, sorry. Here. Copy this LCD out command and you place it here like this. Oh, sorry, I need to here. Now first of all, what you do is that we need only 5 digits, like 2 before the decimal, 2 after the decimal, or maximum 3 after the decimal. So we make it 5 from the 6th. On the 6th column, it should write the percentage like this. And after that, it should remove all the racked backed values. So for that, you copy this. From 7 and onward, it is 8, 9, 10, 11, 12, 13, 14, 15, 16. It will show these bars. So it will not be able to display the noise on the screen. So let's try this on Proteus first. So this is our Proteus. Proteus will debug it. So that will be great when you go to the hardware. It will be very easy for you. Click on run. See, now it is doing exactly what we have been doing in the presentation. Now you can see some stuttering here, but in the actual hardware it will not be shown. So let's get to the actual hardware. So now I rebuild the code. Go to PIC16. Code is build. I build it again. Click on write. Okay, the new code is being written, as you can see. Let it write. Okay, the new code is written. Now you can see, as in the Proteus, it is doing exactly the same, but is not showing stuttering. Now that 78 is changing from 78 to other values is because of the accuracy of this potentiometer. Now I rotate it. You can see that values change with a rotation. 86, and we go down 75, 67, 56, 47, 32, and it does exactly what it needs to do. See guys, our code and programming is working exactly fine as shown in the presentation. Now let me remove this as well, this small noise. Let me show you. Now this is because of some reason called not getting enough time, and also because of the length of this red value. In case of new versions of MikroC for PIC, here in the library, after ADC you have read float to fixed length, or in the conversions you have here to fixed length, float to string like this. There is a float to string. There you go. This float to string has another command called fixed length. With the fixed length, you can trim it to just 5 digits and it will not show their tracked back values. But in our case, we can use some delays. Like you use a small delay after this. 10, and also you give a delay after the value received. Now build this code. It is working fine, that doesn't matter. This is small amount of values which usually come. Let the new code burn. Now see, it will show you some betterment because you had given proper delays. See, now that problem is solved. Now I rotated further, it is going up, and maximum it will go to is 100, like this. So guys, I hope you learned something from this video. Thank you very much for your time, and I hope to see you again. So have a nice day.